Hello and welcome to Easy Projects. So today we're going to talk about op-amps. Why? Because I found that a lot of beginners are actually scared of these and they don't use them. And so was I when I first started, and for a long time I didn't use them either. And today I will show the very basics of what an op-amp is, and it is actually not just some magical device with the two inputs and the magic happens and it will put something at the output. It is a lot more simple than that. And I have some examples of op-amps over here. These are quad op-amps, meaning that there are 4 individual op-amps inside. And these surface mount ones are dual op-amps. Sorry, I actually don't have a single op-amp, but it will work exactly the same, of course. And you can get op-amps in pretty much any package you want. Some op-amps come in a transistor-like metal case, like this one. This is actually a transistor. The op-amp will have 5 legs instead of 3. So if you ever come across one of those, that could be an op-amp. So there is 2 basic things an op-amp can be used for. You can use it as a comparator or an amplifier. There are hundreds of other uses for an op-amp, but they basically build on the same thing. You can make oscillators and so on. So if we take a look at the schematic symbol for an op-amp, it will look like this. Sometimes though, the power rails can be shown as well. So let's connect this to 9 volt and to ground. So if we would use this as a comparator, we would have 2 input signals, one on this pin up here called the non-inverting input and one on this pin down here called the inverting input. And we will of course have to connect something to the output. Let's just put a LED here. Or the schematic symbol would look like this for the LED. And we will connect this through a resistor to ground. So what the op-amp does is it reads the voltage on the 2 input pins. And if this pin, the non-inverting, is higher than the inverting, the output will be on. If the non-inverting is lower than the inverting, then the output will be off. And there is in theory only those 2 conditions. But in practice it is a little different because there is a gain in the op-amp. This is a very huge gain, but if you match these 2 voltages so they are exactly the same, then the output voltage will be somewhere in between the rails. So you can kind of say if what they have written on the symbol here is true, so this is more positive than this one, then the output will also be true or on. There are actually dedicated chips called comparators that will do this better than an op-amp. So you will not find the output in between the rails, it will either be high or low. So now we are kind of moving towards using it as an amplifier. Instead of the 2 inputs we had before, I have connected one to the output, and that is the inverting one, and that is important for this setup. This is in fact an amplifier, but with a gain of 1, so the signal that we send in here will be the same as the one that goes out here. It is still the same thing happening inside the op-amp though. It will still try to set the output high if this one is lower than this one, and if this one is higher than this one, it will try to set the output low. So in this setup it will have to find the spot in between the rails where it will neither be high nor low, as I mentioned before. You can kind of say that the op-amp will set the output so the input voltages match. And another thing to mention is that the input impedance is very high. In other words, very little current will flow into this op-amp. And in most cases you can just say that it is 0, so nothing will go into this. But the output impedance though is fairly low. So you can easily connect an LED or something to the output. That will of course depend on which op-amp you're using. Some might not be able to deliver that much. So that will of course mean that if we put a resistor divider on one of the inputs, that will not affect the voltage in between here. As I said in my resistor tutorial video, if you try to draw current from this node, you will change the voltage. But we just learned that the op-amp will basically not take any current, so I don't think we will even be able to measure this with a fairly good multimeter. In fact, the multimeter will probably take more current than the op-amp when we try to measure it. So you might already have guessed what will happen in this configuration. As I said before, the op-amp will do to the output what it needs to do to set these inputs to be the same, because that is the only situation where that is allowed to have a voltage that is neither high nor low. So we added this resistor divider here. Let's just say the resistors are the same value. That will mean we'll get half the voltage here that we have here. So in order for this input to be the same as this input, we need double the voltage here than we got here. So we just created an amplifier with a gain of 2. And to get another gain, you can just calculate these resistors here, just as you calculate your normal voltage divider. But in most cases, it is not the voltage that you're interested in, it is the actual gain. And that can also easily be calculated by taking the value of this resistor, R2, and divide it by the value of this resistor, R1, and add 1 to that. And I said if these resistors were the same, we would get a gain of 2. So let's try to calculate that. We say they're both 10 kilo ohms, so that will be 10,000 divided by 10,000, and that is 1 plus 1 gives a gain of 2. But the catch comes, say if you try to get a gain of exactly 10. You can easily divide the voltage down 1 to 10 by choosing a 10k here and a 1k here. And if you divide them, that will give 10, but you have to add 1, so you will actually get a gain of 11. So to get the 10, you will actually need a 9 kilo ohm here if you got a 1 kilo ohm here. And that is not a standard value. But you got your 18 kilo ohms, so you can put 2 of those in parallel and get the 9, and then put a 1k here, so that will give a gain of 10. You can also use the first configuration here if you want to be able to draw current from a voltage that you have created with a voltage divider. So you can also tie the voltage divider to the input and use this as a voltage follower. So the voltage here will be the voltage here, but here you are allowed to draw current and here you are not. So we can use this circuit up here to get a current gain with the same voltage as the input. We can use this one down here to get a small signal to look like this. So this is called a voltage follower, and this is called a non-inverting amplifier because it does not invert the signal. So the next one will be an inverting amplifier. It will do the same as this, but it will invert the signal. So instead of looking like that, it will look like that one. And this circuit is an inverting amplifier. And notice I have put the non-inverting input in the bottom this time and the inverting in the top. You can do that just as you want to. Just remember that this is now the non-inverting. So the way this works is we set a voltage on the non-inverting input. And here I have chosen 4.5 volts. We also have 9 volts coming in here. And for the op-amp to get this node down to 4.5 volts, it will have to set 0 volts on the output. And now the inputs will match. But if we drop this to 8 volts, then the output will rise, because it can do with a higher voltage to set this to 4.5 volts. But this circuit is actually a bit more useful if you use a dual supply instead of 9 volts and ground to power the op-amp. So let's try to draw that one. So I have exactly the same circuit, except that I'm powering it from plus and minus 9 volts. And I have 0 volts here. And I have just marked this as ground. So now what will happen if we have 1 volt on the input? The op-amp will try to make this node 0 volts, so it will have to set minus 1 volt on the output. 2 volts here, we still want 0 in the middle, So we'll need -2 on the output. So now it is very easy to see that this is inverting the input signal. And this configuration will have a gain of -1. And to calculate the gain of this will just be R2 divided by R1. So if we lowered R1 to say 1 kilo ohm, then we'll get a gain of 10 instead. And that also makes sense. Say we have 1 volt on the input, and this is now a 1K resistor. We still want to drop this 1 volt down to 0 volts at this mark, but we have to do it through a 10K resistor. So we'll get -10 volts on the output. You might also be able to see that now the input impedance also matters, because if we use a 1 kilo ohm resistor here, and the input impedance is 1 kilo ohm, then this gain calculation will just be garbage, because if we cannot supply enough current, then the voltage will drop anyway and we will get a lower gain. And just to make clear, since we were using ground and 9 volts over here, this input has to be above the 0 volts, of course, so this sine wave will all be above ground. We cannot have a sine wave on the input that is AC and then expect it to work when it comes out the other end, because we cannot go negative with the op amp. So this signal will just be chopped in half, and we will only get the positive of this signal. But if we keep it above 0 volts at all time, there is no problem. So most op amps that we come across will be general purpose op amps. And what this means is basically that you cannot expect the op amp to work up to the rail voltages, or down to the lower voltages as well. So if we take our non-inverting amplifier again, and we make a gain of 2. Now if we put 4.5 volts in here, we would expect 9 volts on the output, but we will not get that. Depending on the op amp, we will get as much as 2 volts lower than that. It is not because there is an error in the gain, it is just that the op amp cannot go up to the rail voltage. So say if we put 3 volts into the input, we can easily get 6 volts out on the output. But once we hit a certain point, the output cannot go higher. And there might be some non-linearity up in that region, I'm not sure about that. It will be the same if we put 0 volts in here. A gain of 2 should still give us 0 volts on the output, but we might expect to get 1 volt here if we use a general purpose op amp. If you have seen my transistor tester video, I have already shown another problem with those general purpose op amps. If we use it as a comparator, then it will easily tell the difference between, say, 4 and 4.5 volts, or even 4 and 4.001 volt. But it will not be able to tell the difference between, say, 1 and 1.2 volts. So the output could be high when it should have been low, or low when it should have been high, or it can be somewhere in between the rails. There is practically no way to know that. It might tell in the datasheet, or you should just not use the op amp down there. In my experiment I had a voltage of 1.4 volts, I think it was, on one of the inputs, and I dropped the other input down, and I was expecting it, or I hoped it would change when it reached 1.4 volts, but it didn't. It changed already at 1.7 volts. But that is not all of the story, because if that was it, I could live with it. It would just be lagging a little bit. But when I dropped it even further, the output went up high again. So that is also something to watch out for. So even though you have, say, 5 volts on the non-inverting and you have 4 volts on the inverting, that will make the output high, of course. And if you drop the inverting input, you wouldn't expect anything to happen. But if you drop the inverting input far enough, it might actually affect the output, if this gets close enough to the negative rail. Or in my case, it was the other way around. I kept the inverting input high, and I say this was at 3 volts. And I dropped this one, and it sure enough went low when it dropped below the 3 volts. But when this one got near the negative rail, or the ground here, it turned the output back high. It doesn't mean that you cannot use it, because you can just put a negative 9 volt rail here, and now you can easily work around the 0 volts. And also, if you need to go to 9 volts, you can just put a 12 volt up here. If your op amp can handle that, of course. And this will be the same thing for the output at this one here. If we power it from minus 9 volts, then of course we can easily get 0 volts at the output. And it will first be a problem when we reach either plus 9 or minus 9 volts, or near those rails. Of course, someone found this very annoying, including me. So someone invented the rail-to-rail op amp. And no, that wasn't me. But in most of these op amps, you will only get one of the things. So you will either get rail-to-rail output or rail-to-rail input. So the rail-to-rail input will be able to tell the difference between the inputs all the way to the rails, and the output will not be able to go to the rails still. On the rail-to-rail output one, it will not be able to tell, or it may not be able to tell the difference between the inputs at either the high or the low rail, but the output will be able to go to 9 volts and to ground. So if you use this as a gain amplifier, where you had an input signal swing of plus minus 1 volt, that is far within the rails, but we have a gain of 10. The output voltage will be able to reach both plus 9 volts and minus 9 volts. But the amplifier will of course clip, so it will make a like that on the sine wave, because this is too high when the gain is applied. So it will hit these two rails, but we can do that with a rail-to-rail output. And now comes the real expensive stuff. If you want an op amp that can take the inputs to either rail and take the output to either rail, that is called an rail-to-rail input-output op amp. And you can easily pay $5 to $10 for one of these, but they are quite good. Another thing to keep in mind is what is called input offset voltage. And that basically means that the op amp will read an error on either of the pins. So it will think that 1.001 volt might be equal to 1.0005 volts, or something like that. For these more expensive op amps, it is typically less than a millivolt. And that can be down to nanovolts if you really dig up the gold. But say there is an error of 500 microvolts, and that is nothing really. And that could be used for perhaps 95% of all you can think of. But if you have a very high gain on one of these amplifiers, then this input offset voltage gets multiplied as well. So if you have a gain of say 100, so now instead of 500 microvolts, we'll get 50 millivolts. So that could perhaps be a problem. So I think that what most people are getting wrong is they have a general purpose op amp, and they are not aware that it cannot go to either of the rails. And I can remember I had problems with that when I bought my first op amp and was playing around with that. And that was in fact one of these TL074s here. So if you just keep this in mind, it probably shouldn't be a problem. So I hope that was useful in some way and it wasn't too confusing. I am planning to make a video where I build up a whole bunch of op amp circuits and try to explain how they work and how to calculate the resistors used and so on. And there we will also go into differential amplifiers. I didn't mention those in this video, but you can also make that with an op amp. And that will basically measure the difference between the inputs and put that on the output. So if you liked the video, please give it a thumbs up and subscribe to my channel. And if you have any ideas to some funny op amp circuits, you can post them in the comments and I will take a look at that. So So thanks for watching and see ya!